In this lecture, we will cover factors and divisibility, prime numbers, prime factorization, the greatest common divisor of two numbers, and the least common multiple of two numbers. We will begin this section with factors and divisibility. A factor of a number divides that number with a remainder of 0. For example, 5 is a factor of 10 since 5 will divide into 10 with a remainder of 0. Another way of stating that 5 is a factor of 10 is to say that 10 is divisible by 5. 5 divides into 10 2 times. That means 2 is also a factor of 10. Another way to state this is to say that 5 will divide into 10 evenly 2 times. We will look at some examples. What are the factors of 9? It is important to remember that 1 is a factor of every number. Also, for every number except 0, the number itself is a factor. If a number has more factors than 1 in itself, that means there are other numbers that will divide into it with a remainder of 0 or divide evenly into it. Therefore, the factors of 9 are 9 and 1. Also, since 9 is divisible by 3, and 3 times 3 is 9, 3 is a factor of 9. For our next example, what are the factors of 30? As stated before, every number will have 1 and itself as factors. So 2 of the factors of 30 are 1 and 30. 30 is also divisible by 2, and 2 divides into 30 15 times. This means that 2 times 15 is 30. Therefore, 2 and 15 are factors of 30. Furthermore, 30 is divisible by 3, and 3 divides into 30 10 times. So 3 and 10 are factors of 30. Finally, 30 is divisible by 6, and 6 times 5 equals 30, so that 5 and 6 are factors of 30. Notice that 9 has 3 factors and 30 has 8 factors. The number of factors will vary. For instance, the number 31 has only 2 factors, and 31 is considered to be a prime number, which we will discuss later in this presentation. There are simple tests known as the divisibility test, used to determine if a given number is divisible by the numbers listed in this table. We will cover each number listed in the table, giving the test and an example. A number is divisible by 2 if the last digit of the number is divisible by 2. In order for the last digit of any number to be divisible by 2, the last digit of the number must be 0, 2, 4, 6, or 8. When a number is divisible by 2, the number is considered an even number. An example, 1570 is divisible by 2 since the last digit is 0, which makes the number even. When we divide 2 into 1570, we get the quotient 785. A number is divisible by 3 if the sum of the digits is divisible by 3. An example, 642 is divisible by 3 since the sum of the digits 6 plus 4 plus 2 equals 12, and 12 is divisible by 3. When we divide 3 into 642, we get the quotient 214. A number is divisible by 4 if the number formed by the last 2 digits is divisible by 4. An example of this one, 17,816 is divisible by 4 since the last 2 digits of the number form the numbers 16 which is divisible by 4. When we divide 4 into 17,816, we get the quotient 4,454. A number is divisible by 5 if the last digit is 0 or 5. An example of this one, 2,685 is divisible by 5 since the last digit is 5. 2,685 divided by 5 gives us a quotient of 537. A number is divisible by 6 if the number is divisible by both 2 and 3. An example of this one, 30,504 is divisible by 6 since the number is divisible by both 2 and 3. Notice that the last digit of the number is 4, which according to the first test tells us it is divisible by 2. And notice also that when you add the digits of the number, you get 12, which is divisible by 3. Therefore, the number itself is divisible by 6. When we divide 6 into 30,504, we get the quotient 5,084. A number is divisible by 8 if the number that is formed by the last 3 digits is divisible by 8. An example of this one, 9,160 is divisible by 8 since 160 is divisible by 8. Notice that 16 is divisible by 8, and 160 is 16 followed by 0. When a number is divisible by 8, and it's followed by only zeros, then the number which includes zeros is also divisible by 8. When we divide, we get the quotient 1,145. A number is divisible by 9 if the sum of the digits of the number is divisible by 9. An example of this one is 46,314. This number is divisible by 9 since the sum of the digits is equal to 18. 18 is divisible by 9, therefore the number itself is divisible by 9. When we divide 9 into 46,314, we get the quotient 5,146. For the last one, most of us probably remember this from elementary school. A number is divisible by 10 if the number ends in 0. An example of this one is 1,574,290 is divisible by 10 since the last digit is 0. When we divide 10 into the number 1,574,290, we get the quotient 157,429. These divisibility tests may be helpful in many ways, but in particular in reducing fractions to lowest terms and factoring. Try testing yourself by making up numbers that follow the guidelines of these tests. We will now look at 3 examples in which we will apply the divisibility test. For our first example, which of the following numbers are divisible by 2? According to the first divisibility test, a number is divisible by 2 if the last digit of the number is divisible by 2. The digits that are divisible by 2 are 0, 2, 4, 6, and 8. When a number ends in one of these digits, the number is considered even. Therefore, the numbers from the list that are divisible by 2 are the even numbers 18, 44, 170, and 1,796. For our second example, which of the following numbers are divisible by 3? According to the divisibility test, a number is divisible by 3 when the sum of the digits of the number is divisible by 3. Therefore, the numbers that are divisible by 3 are 75, since the sum of the digits of the number is 12, and 12 is divisible by 3. 378, since the sum of the digits of this number is 18, and 18 is divisible by 3. And 1371, the sum of the digits of this number is 12, which of course is divisible by 3. For our last example, which of the following numbers are divisible by 5? According to the divisibility test, a number is divisible by 5 when the last digit of the number is 0 or 5. The numbers divisible by 5 are 100, since the last digit of the number is 0, 45, since the last digit is 5, 195, again last digit is 5, and 2230, since the last digit is 0. We will now consider prime and composite numbers. We will start with the definition of a prime number. A prime number is a natural number greater than 1, which has only itself and 1 as factors. The definition of a composite number is a natural number greater than 1 that is not prime. We will consider an example. Which of the following numbers are prime, which are composite, and which are neither? We will begin with the prime numbers. Notice that the first number in the list is 1. 1 is neither prime nor composite because prime numbers are greater than 1 and composite numbers are greater than 1. Therefore, 1 is neither prime nor is it composite. The second number is 2. 2 is a prime number. It is important to note that 2 is the only even prime number. The next prime number is 5, then 11, 13, 17, 23, and 41. The only factors of each one of these numbers is 1 and itself. We will now list the composite numbers. The composite numbers may also be defined as having more than 1 and itself as factors. Therefore, the composite numbers are 6, 10, 15, 27, 38, and 77. Try to test your knowledge by finding another factor for each one of these numbers. Finally, as mentioned before, the natural number 1 is neither prime nor composite, according to the definitions of prime and composite. We will now look at an example of finding the greatest common divisor and the least common multiple of two numbers. We will use what is known as prime factorization to find the GCD and the LCM of two numbers using a factor tree. For our example, we will use prime factorization to find the GCD and the LCM of 216 and 252. We will start with finding all the prime factors of 216. Since the last digit of 216 is an even number which is divisible by 2, the number itself is divisible by 2. When we divide 2 into 116, we get 108. That means 2 times 108 equals 216, and 2 and 108 are factors of 216. So we can write 2 and 108 as the first two branches of our factor tree. Notice also that 108 is divisible by 2, and when we divide 2 into 108, we get 54. That means that 2 times 54 is 108. Therefore, 2 and 54 are factors of 108, and can be put on our factor tree. Notice also that 54 is an even number, therefore it is divisible by 2. 2 divides into 54 27 times, so that 2 times 27 is 54, so 2 and 27 are factors of 54. It should be obvious that 27 is divisible by 3, since 3 times 9 equals 27, and this is a simple multiplication problem. But if you do not recognize this common multiplication problem, we may apply the divisibility rule that states if the sum of the digits is divisible by 9, then the number itself is divisible by 9. And since the sum of 2 and 7 is 9, which of course is divisible by 9, we know that 27 is also divisible by 9. Since 3 times 9 equals 27, they are both factors of 27. Therefore, 3 and 9 can be put on the factor tree. Finally, since 9 is divisible by 3, and 3 times 3 is 9, the next two branches will both be 3. Since the last two branches are both 3, and 3 is a prime number, we can stop. Next, we will find all the prime factors of 252. 252 is an even number, so it is divisible by 2. 2 times 126 equals 252, so 2 and 126 are factors of 252, therefore can be on the factor tree. Then 2 will divide evenly into 126 63 times, so that 2 and 63 are on the factor tree. Notice that 63 is divisible by 3, and 3 divided into 63 is 21, so 3 and 21 are on the factor tree. Finally, 3 will divide into 21 evenly 7 times, so 3 times 7 is 21. Therefore, the last two branches of our factor tree are the prime numbers 3 and 7. We may now write the prime factorization of each number. The prime factorization of 216 is the product of all the prime numbers that are on the outer edge of the factor tree, which I have circled in red. That is, we write the product of all the prime numbers that are circled in red, giving us the prime factorization of 216. We find the prime factorization of 252 by finding the product of all the prime numbers that are circled in red on the factor tree. To find the greatest common divisor of the two numbers, we write their prime factorizations. Then we look for all the prime numbers that divide both numbers at the same time. That is, we look for the prime factors that the two numbers 216 and 252 have in common. Notice that they have 2 2's in common and 2 3's. The GCD is the product of all the prime numbers that these two numbers have in common. So the GCD is 2 times 2 times 3 times 3, which is 36. When we find the least common multiple, we are finding the smallest natural number that is divisible by both numbers. We look for the largest number of times that each prime factor appears in the factorization of the number, and then we multiply those numbers. To find the LCM of these two numbers, notice that the number 2 appears 3 times as a prime factor of 216, and only 2 times as a factor of 252. So we use 3 2's since we are taking the greatest number of times the prime factor appears in either number. Furthermore, Notice that the number 3 appears 3 times as a prime factor of 216 and appears only 2 times as a prime factor of 252. So we will also use 3 3's. The only other factor that appears in either number is 7. So we will use 7 since we must use all the prime numbers that appear in either number. Therefore, we find our least common multiple by multiplying the numbers that we have in blue, giving us the least common multiple, 1512. We will now use prime factorization to reduce a fraction to lowest terms. In our first example, we will find the prime factorization of 216 over 252. And then reduce the fraction to lowest terms. In essence, finding the prime factorization of the numerator and denominator will allow us to determine the greatest common divisor of the two numbers. This is very useful when the numerator and denominator are large numbers. In our previous slide, we found the prime factorization of 216 and we found the prime factorization of 252. And then we found the greatest common divisor, or GCD, of the two numbers. So our fraction 216 over 252 may be rewritten using the prime factorization we found in the previous slide of these two numbers. We now cancel the common terms. In the numerator and the denominator, we have two 2's that are in common. We also have two 3's in common. We are left with 2 times 3 over 7, which equals 6/7. Notice that when we multiply the numbers that the numerator and denominator have in common, we get the greatest common divisor, which is 36. So we can divide both the numerator and denominator by the GCD 36. So another way to reduce this fraction is to divide 36 into both the numerator and the denominator, giving us 36 times 6 over 36 times 7, leaving us with the reduced fraction 6/7. Therefore, 216 over 252 in lowest terms is 6/7. We will look at one more example. We will find the prime factorization of 30 over 84 and then reduce the fraction to lowest terms. We won't actually do the steps of the prime factorization. We will just rewrite 30 and 84 using their prime factorizations. Notice the numerator and the denominator have 2 in common, and they have 3 in common, leaving us with 5 over 2 times 7, giving the reduced fraction 5/14.